When it comes to setting the stage, factors such as sound are key to the initial impression. The sound of heels is synonymous with authority, confidence, and a certain type of allure, announcing some grand arrival. But for women, heels are also synonymous with pain, lack of stability, and long-term side effects. To fix this, designers stress the importance of structural integrity and support of the shoe, honing the craft through a decades-long design process and nowadays, stimulating stress conditions to validate consumer concerns. Today, we aim to replicate this and introduce to you the optimal heel from the eyes of the researchers who also happen to be designers.
As we are currently studying the heel, we only needed to model the back part of the high heel. This model was constructed in AutoCAD Inventor, where each part of the measurements were parameterized to create a transformative heel. By changing the heel height, the width, and the position, we were able to modify various parameters while keeping everything else constant, successfully isolating the various conditions and demonstrating the influence of each parameter. The geometry is crucial to the design of the heel, and was a process that we spent the most time and resources on. Research online and real-life measurements were used as references in our model.
After importing this into ComSol and using the Live Link feature, we are able to access all the variable parameters used in the modeling process. We will be doing a structural mechanics analysis on the model and analyzing these physics. Heel failure is determined by von Mises stress. This is the value of stress that an object can withstand before it yields, or in this case, fails. Physically, this would mean that the heel would have broken under a certain amount of force. The buckling study predicts the load at which a structure becomes unstable and collapses suddenly, even if the material has not yet reached its yield strength. Physically, buckling occurs when the potential energy of an external load is greater than the strain energy the structure can store by bending. Buckling is a bifurcation problem, meaning that there is more than one possible equilibrium state. At a certain load, the structure can either stay straight, unstable, or snap into a bent shape, which is stable. This study will find that tipping point. The physics themselves are relatively straightforward, until it breaks. But then comes the matter of parameters and force calculation. As mentioned before, the study will analyze the effects of heel height, heel width, and heel position. Lower, thicker heels would mean lower center of gravity and more stability. But we want to investigate where these weak points actually occur and potentially what materials we would need for these regions. Varying the parameters will also highlight the greatest rate of change, a design boundary with risks.
The force that you apply downwards is not just the simple half of your body mass, but this is a value that changes because of something called the gait cycle. During the gait cycle, there are three important stages: heel strike, mid stance, and toe off. During heel strike, only the heel comes into contact with the ground. Afterwards, body weight is gradually distributed across the bottom of the foot until it is even, which marks as mid stance. Then the body weight starts to transfer to the other foot until the original foot leaves the ground. This is the toe off. To investigate the effects of different parameters on the stress on the heels of stilettos, we will be focusing on heel strike and mid-stance only, since the heels are not involved during toe-off. Naturally, the physics behind the force of each step varies depending on the footwear. Much public research exists for both athletic footwear and fashion footwear alike, and we combed through many articles to determine a reasonable force vector that we can apply.
Let's run through the math. The average woman weighs 78 kilograms. In terms of force, that's 765 newtons. Bay et al. Claims that when wearing high heels, 23.5% of the pressure is absorbed by the rear heel. This means that taking into account the surface area of the model, the force absorbed by the heel over the area of the heel is 82 kilopascals, felt in the negative y direction when standing upright and at a 60-degree angle when taking the initial step. It is also important to clarify that this model will align with current manufacturing materials used, that is, ABS plastic for most of the heel. Let's take a look at our results. In mid-stance, we assume that the entire body weight is extended onto one foot. To stimulate the mid-stance of the gait cycle, we apply the force onto the sole base and set a fixed constraint on the bottom surface of the heel, as this part will remain stationary at the stage.
Stiletto heels typically range from 60 to 120 millimeters, but we tested a wide range of values. In the parameter sweep, the von Mises stress is always beyond yield, indicating that the heels are difficult to break in this vertical position. The influence of the height of the heel is nonlinear and inconclusive, but is significantly below yield, so the previous conclusion holds. When comparing the heel heights, it appears that failure typically occurs at the pitch, where heels often snap off. There also appears to be deformation affecting the inner flat surface of the heel, indicating that the heel fails by collapsing inwards. Let's analyze the width or diameter of the heel. Stilettos are characterized by the thin pin-like heel, with diameters ranging from 5 to around 12 millimeters. Quite predictably, the thinner the heel, the higher the stress and greater the fragility. The interval ranging from 5 to 6 appears to have the greatest influence on the yielding behavior of the heel. Thinner heels appear to have greater weakness at the pitch, a previously identified weak spot. Finally, the position of the heel determines where it is located relative to the force being applied. Our current model aligns the axis of the heel and the sole. In practice, many designs shift the position further back, maximizing the distance between the tip of the shoe and the heel. A direct collinear force appears to minimize the von Mises stress, indicating that the optimal position of the heel occurs when it is directly aligned, evenly distributing the force onto the entire heel.
The greater the critical load factor, the more stress the structure endures before buckling may occur. In terms of heel height, there's a dramatic decrease in stability between 60 and 70 millimeters, with a negative trend indicating that the shorter heel is more stable, as less deformation propagates through the heel. Consistent with the von Mises stress, thicker heels, particularly in the 9 to 10 millimeter diameter range, are more stable compared to any other range, as this interval has the most dramatic increase in critical load factor. Finally, farther alignment appears to offer more stability, which contradicts to the previous study, where coaxial alignment makes the heel strongest. This is likely due to the strength from the shear alignment coming at a cost for better rotational equilibrium. In walking conditions, we must also consider the heel strike. Here we assume that half the body weight would be exerted onto the rear edge of the heel, looking specifically at the moment where the heel makes a 60-degree angle with the ground. Half the force over area, factoring the cosine ratio, gives the amount of shear pressure going parallel to the ground, while this force, factored by the sine ratio, gives the amount of pressure going perpendicular into the ground. We will simulate this stage of the gait cycle by fixing the rear edge of the heel and applying pressure at an angle.
Repeating the parameter sweep shows that it follows the same overall trend as mid-stance. The taller and thinner the heel is, the easier it is to break. The height has a linear relationship with the stress, while the diameter has a more exponential relationship. For a heel taller than 7 cm or with diameter smaller than 15 mm, it can be at risk of breaking upon striking near the point of contact with the ground. This border probably includes most stilettos, and that's because the pressure from heel strike is way larger than that from mid-stance. As of heel position, the coaxial alignment still minimizes the stress.
When analyzing Euler buckling for heel strikes, once again, there is an early dramatic decrease in stability. The negative trend indicates that shorter heels are more stable. This consistent trend indicates that the angle of the force from the gait stage does not impact the resulting reaction, as the heel will still become less stable with height and buckle easier. Similarly, thicker heels, again in the same range, are the most stable as they require the most force to cause buckling. Finally, heel position once again demonstrates a relation consistent with previous results. Even during a heel strike, farther alignment appears to offer the most stability.
To maximize profit, manufacturers tend to cut down on the sturdy materials, opting for plastics or imitation materials lacking the structural integrity of high-quality craftsmanship. But this is no excuse to sacrifice quality for profit, as according to a study investigating the increasing trend in high heel-related injuries, 19% of foot-related common injuries have been linked to broken heel-related causes. Using a steel core within the heel has been a useful solution, but with the addition of this part comes countless optimization problems and further testing needed. Is there any way to fix these structural issues while still maintaining the elegance of a stiletto? Let's look at a market example.
You might have heard about a certain brand called Louboutin with an iconic red sole and a massive $75 million revenue. But money aside, their reputation and legacy inspires a younger female generation. Their Socate stands at 120 millimeter height and is considered a classic fashion staple. But this model is infamous for its thin, unstable heel and extreme lack of comfort. The Messi is lower at 100 millimeter height and is a newer model with a thicker heel designed to be more stable. This was the company's answer to the concerns of the Socates, a response that drove sales towards a larger market, allowing people with previous stability and structural concerns to enjoy the power that comes with owning a pair of Louboutin stilettos. This research is both needed, has a high profit potential, and explores a field of innovation that has existed decades prior to and continues to flourish in upcoming years. Structural mechanics is not just analyzing buildings and completing truss problems, but it can take a fashionable form of problem solving that appeals to both aesthetics and physics.